Proof by contradiction is usually the hardest proof technique to grasp. It constructs a proof that we call non-constructive. And there was a time when proof by contradiction was a highly controversial type of proof, when mathematicians didn't really believe that these were legitimate proofs. But now it is a widely accepted way of proving things. But it is still very difficult. So take the time understanding what this is saying. What is the idea behind proof by contradiction? So suppose you're trying to prove a statement, let's say P. Then in proof by contradiction, what we do is we assume not P and try to arrive at a contradiction. And what does it mean to arrive at a contradiction? To try to derive an absurd statement. This will become clear when I do examples. So what we're saying is, if I assume not P, then I am reaching an absurd statement. So P must have been true to begin with. So this is the structure of a proof by contradiction proof. Something useful to remember here, recall that if you have not P implies Q, then I can write this as not of not P or Q by conditional identity. And this can then be expressed as not P and not Q. This is De Morgan's laws. And then not P becomes P and not Q. So when you have an implication of the form P implies Q and you're trying to prove it by proof by contradiction, then you assume its negation, which is P and not Q. With this, let us do some examples. Suppose you're trying to prove a very basic fact that there is no largest natural number. I mean, this is a trivial statement. There is no secret to this. There is no largest natural number because they keep on increasing. But that is not a mathematical proof. Mathematical proof has to be completely rigorous, something that anybody can verify without a shadow of doubt. So I want to prove this by contradiction. So I'll assume the opposite of this. So I'll assume in my hypothesis that there is a natural number, which is largest. And here I'm not trying to get to any conclusion. I'm just trying to reach at some absurdity. Let's call this, let's give it a name. Let's say M. And this means that M is greater than or equal to N for every natural number. But now where is the absurdity here? This is still fine. Well, but M plus 1 is itself a natural number. So I can choose this to be my N. And then I get M is bigger than or equal to M plus 1. And now this is the absurd statement. It is not true that M is bigger than or equal to M plus 1. And so we have reached a contradiction. Then we write it as a formal proof, the same way we written proofs earlier. We say we'll do proof by contradiction. So we assume the opposite, that is, suppose there is a largest natural number M. Then M is greater than or equal to N for every natural number N. And in particular, we get M is bigger than or equal to M plus 1. But now this is not possible. We have reached a contradiction. And so our assumption must have been false. And what was what was our assumption? Our assumption was, suppose that there is a largest natural number, and that must have been false. and hence there is no largest natural number. That's an example of proof by contradiction. Now let me do a slightly harder example. Show that there are no positive integers x and y such that x squared minus y squared equals 1. So I'm trying to show that there are no positive integers x and y. So maybe let me try to suppose there were positive integers x and y such that x squared minus y squared equals 1. So this is now my assumption, it's my hypothesis. And I'm not trying to reach a conclusion, but I'm trying to reach an absurdity. Well, then what happens? This gives me x minus y times x plus y equals 1. Now, the only way you can write 1 as a product of two numbers is either 1 times 1 or minus 1 times minus 1. So this gives me either x minus y is 1 or now I can subtract the two equations. So let me focus on the left ones. I can subtract them and I will get minus 2y equals 0. That gives me y equals 0. And if I do it on the right side, I get 2y equals 0, minus 2y equals 0, y equals 0. So in both cases, I'm getting that y is 0. But one of our conditions is that x and y are positive. So that's how I'm reaching a contradiction. And I'll now formalize this. So we'll do proof by contradiction again. Suppose it is the case that there are positive integers x and y such that x squared minus y squared equals 1. This will give me now both of these. But now this is a contradiction. To the positivity of y. Contradiction is here. And so our assumption must have been false. Hence, there do not exist positive integers x and y such that x squared minus y squared equals. There are infinitely many primes. There are dozens and dozens of proofs of this. And this one is a proof that was given by Euler. So what's the idea? Let me do some scratch work. Suppose this is false. Suppose there are only finitely many prime numbers. Let's suppose that these are all the prime numbers. If these are all the prime numbers, then every integer must be divisible by at least one of these. Because we have prime factorizations, and every integer can be decomposed as a product of primes. And if these are all the primes, then every integer must be divisible by one of these. And so the idea is to come up with an integer which is not divisible by one of these. And there are many, many ways of doing this. The simplest or one of the possible candidates is to take n equals their product and then just add a 1 to it. N minus 1 is p1, p2, pn. And so pi divides n minus 1. And if we have pi divides n and pi divides n minus 1, then I'll get pi divides 1. But you cannot have a prime number dividing 1, and we have reached a contradiction. So this is Euler's way of proving this. So we'll prove a contradiction. Suppose there exist only finitely many primes. Say P1, P2, Pn, where n is a positive, n is a natural number. Every integer m is divisible by one of these pi's. In particular, m is equal to p1 times p2 times pn plus 1 is divisible by at least one of the pi's. So let's say pi divides m, but pi divides p1, p2, pn. So pi divides the difference, which is 1. But pi is a prime number, and we are saying a prime number divides 1. This is not possible. So our assumption must have been false. And what was our assumption? We had assumed that there were only finitely many primes. And so there are infinitely many. This is a very classic proof by contradiction.